Hello all. So in the last class we were discussing about K-maps, right? So we have looked into how do we solve K-maps for reducing the, how do we use K-maps for reducing the Boolean expression. We have seen 2 variable K-map, 2 and 3 variable K-map along with 4 variable K-map. Today in this session we will continue with the K-maps wherein we will be discussing about 5 variable K-map, okay. So I will be discussing about 5 variable K-map and then we will also look into NAND and NOR implementation. As I explained you in the earlier classes, we go for NAND and NOR implementation, which are universal gates. We make use of universal gates to reduce any Boolean function such that the number of logic gates that we use will be reduced, okay. So let's get into the class session. Yeah. So we'll start with 5 variable K-map. So 5 variable K-maps in the sense we have 5 inputs in the given expression or in the given Boolean function, and we use this K-map procedure for reducing the given function which has 5 variables in it, okay. So basically as discussed, the number of cells in the K-map depends upon number of inputs, right. So as we have 5 variable K-map here, the number of cells that we have are 32. Okay, and each of the cell will have either minterm or maxterm. This rule is the same, it is not changed, okay. Now if the Boolean function is represented in SOP form, then we have minterms in the cells, and we have Boolean function represented as POS form, we have maxterm represented in the cells, okay. So the minterms are represented from M0 to M31, where M0 is corresponding to A bar, B bar, C bar, D bar and E1. Okay, and M31 represents to A, B, C, D, E. Minterms are nothing but the product terms. Please remember. So that is the reason I am taking a product term with 5 variables which are A, B, C, D and E. On the other hand, if you are going for 5 variable Boolean function reduction using POS, then we have max terms representations which are represented by capital M, 0 to M31, where M0 represents, this is sum term, right. So A plus B plus C plus D, and M1 represents A plus B plus C plus D plus E bar, and then M31 represents A bar plus B bar plus C bar plus D bar plus E bar. So one change that you can observe is here 0 represents complement for the product term, here 0 represents the original literal or original term for the sum term, okay. Now all these 32 cells of the 5 variable K-maps are divided into 2 blocks, okay. So far whatever we have seen was only 16 cell K-map, right, that is 4 variable K-map, but here for 5 variable K-map, okay, we have 2 blocks of 16 cells each, okay. Make note of this, this is very important. I have 2 blocks of 16 cells each, and the first block I write it as A, which I give it as 0, and the second block I write it as A, which I give the term as 1, okay. Please make a note of this. The 32 cells of the 5 variable K-maps are divided into 2 blocks of 16 cells each, which are arranged side by side. As you can see in the figure, there are 2 blocks of 16 cells each arranged side by side, and the left block represents the minterms from M0 to 15. Okay, the left block represents the if you are taking SOP, we have minterms from 0 to 16 on the left block. On the right block, I have from 16 to 31. Okay, observe this. Okay, on the right block I have, this is 16, sorry, there is a mistake, this is not M0, this is 16, M16. Okay, on the right block I have from 16 to 31. Okay, so I have these 2 adjacent blocks. Okay, now how do I do mapping? So one change that you observe here is A is 0 in the first block, A is 1 in the second blocks. The other 4 inputs B, C, D, E are represented commonly for the 2 blocks. That is, I have B, C, D, E here, B, C, D, E here with only change of A. Why? Because when we observe the representation, when we observe the binary representation of 31 variables, how do we have them? We have it from 0, 0, 0, 0, 0. If we take 5 variables A, B, C, D, E, 0 will be represented something like this, 1 will be represented from 0, 0 to 1. Similarly, 15 will be represented from 0, all ones. Starting from 16, I have 1 0 0 0, 1 0 0 1 and so on till 1 1, 1, 1, 1, which will be 31. So once you observe this particular pattern, the input A is 0 for BCDE starting from 0, 0, 0, 0 to 1, 1, 1, 1. When you go for 16 to 31, that is the second block, input A is 1 with these 4 inputs, with other 4 inputs represented as 0, 0, 0, 0 to 1, 1, 1, 1. Okay. So BCDE are common for both the blocks, only A is different. That is the reason I keep A is equal to 0 with BCDE and A is equal to 1 with BCDE. Okay. Here the minterms are represented from 0 to 15. Here the minterms are represented from M16 to M31. Okay. So this is how we designed the 5 variable K map. Okay. Now when we talk about grouping, okay, so once we finish drawing the basic structure of the K map, we would go with grouping. Okay. Now let's see how do we do the grouping process. Okay. Now in the 5 variable K map, we can form 2 squares, 4 squares, 8 squares, 16 square or 32 squares by involving 2 blocks. Okay. So when you take these blocks, okay, you can have 2 power n combination of squares. That is, you can have 2, 4, 8, 16 or 32 square, which involves both the blocks. Also, squares are considered adjacent in these 2 blocks. Okay. Now, when one block superimposes on the top of another, both the squares that we are mapping would be same. Okay. You would understand that once we get into the example. Okay. Yeah. Now when we go for POS representation of 5 variable K map, okay, what is the change here? Instead of small m representation, I have capital M, and those will be the product terms and these capital M's would be the sum terms. Okay. Now let's solve the problems of 5 variable K maps. Okay. Now let's see some examples. Here in the example 1, I want you to reduce the 5 variable boolean function in SOP form. So when I talk about SOP, I have summation of n, okay, using 5 variable K map. Here the 5 variables are A, B, C, D, E, and the number of minterms that are given are represented in the given function. Okay. Now how do I do that? First I draw the basic structure of K map representing A is equal to 0 block, A is equal to 1 block. In step 2, what do? I place all these minterms inside the K maps with one label. As I told you, minterms are represented with ones inside the cells of K map, whereas max terms are represented with zeros inside the K maps. Okay. Now when you look into this, okay, so I have placed 0, 1, 2, 4, 7, 8, 12, 14, 15 in the first block, and in the second block 16, 17, 18, 20, 24, 28, 30, 31. Okay. Once I am done with placing, I will go for grouping. Third step is grouping. Okay. Now in the grouping, look into the grouping of 5 variable K map. As you can see, cell 0, 1, 16, 17. 0, 1, 16, 17 will form a 2 square, right? 0, 1, 16, 17 will form a quad. Okay. Now when you look into this particular quadding, what I want you to understand is, here A is equal to 0, here A is equal to 1. So A, 0 and 1 gets cancelled, and the output term or the resultant of this grouping would be, here it is 0, 0, 0, 1, wherein 0 and 1 gets cancelled, right? So I am left only with D bar. Okay. So I will have, this is commonly shared with B bar, C bar, right? So I will have B bar, C bar and D bar. Why am I having it as B bar, C bar, D bar? This is B and C, sorry, B bar, C bar, 0, 0. Here it is D bar, E gets cancelled because 0 and 1. A naught and A1 gets cancelled because this particular grouping is common in A and A is equal to 0 and A is equal to 1, that is both the blocks. So the output of this expression would be, B bar, C bar and D bar. Okay. Now look into the second grouping. Cell 0, 4, 12, 8, 16, 20, 28, 24 are the same, right? So in both the cases, A is equal to 0, A is equal to 1 gets cancelled. 0 0 1 1 0 1 1 0 of BC gets cancelled and I will be left only with D bar E bar. So for that grouping my output will be D bar E bar. Okay. Next look into this. Cell 2 and 18 form a pair. Cells 2 and 18 form a pair wherein the answer is what? B bar C bar and the answer is B bar C bar D E bar. Okay, A and A naught gets cancelled here. Okay, so the output of this grouping would be B bar, C bar, D and E bar. Okay, now when you look into cell 14, 15, 31 and 30, okay, both of them are in the same thing. So A naught and A bar gets cancelled. I will have BC, here E gets cancelled. Okay, B, C, D. That grouping result would be B, C and D. Now there is one thing which is not common in both. What is that? Cell 7 and 15. Okay, cell 7 I don't want to go for isolated one because I can pair 7 with 15. So I'll make a pair. Now this particular pairing is not available in this. So I have to consider A also. So what would be the output of that cell? The output of that cell would be A bar and then look at BC. Look at this 715 BC water covering. B gets cancelled because this is 0 and 1. So I'll have A bar C and 715 is covering this particular column, that is D and E. D and E. So this would be the result of this particular when you look into this 0 2 16 18, okay, so that is that one. So wherein we will be cancelling D. Okay, so this is what. Okay, now in short, look at the board now. I have first grouping which is covering cells 0. I have the next slide which is detailed. Yeah, look at this. There are no isolated ones. Okay, my answer is there are no isolated ones in the K map. Second thing is the minterm M4. Okay, look at this. 0, 4, 8, 12, 16, 20, 28, 24 are together. Okay, so that is D bar E bar. That is D bar E bar. Okay, next 0, 1, 16, 17. 0, 1, 16, 17, A naught, A1 gets cancelled and the result of that particular thing is B bar, C bar, D bar. Okay. Now when you look into these cells 0 to 16, 18, 0 to 16, 18, A and A bar gets cancelled, B bar, C bar and then I'll have E bar. Okay. Now next minterm 7 and 15. Here minterm 7 and 15 are not available in this. Okay, so I will consider A bar. Okay, and then minterm 7 and 16 are covering D and E, and here they are getting B and B bar are getting cancelled and will have C. Okay, similarly 14, 15, 30, 31. 14, 15, 30 and 31 will form a 4 square. So we will have that output as BCD. So finally how would I write the expression? As this is SOP, I am adding the product terms of all the groups and making it into a SOP. Sum of the product groups which I have generated from the grouping. Okay, so this is how we solve 5 variable K map, Boolean function with 5 variable K map. Okay, now let's look into second example. I have POS equation here. Okay, so how do you differentiate POS in SOP? Pi capital M. Okay, now what is the second difference? I will place this 2 block 16 cell each K map for designing 5 variable K map, and then I will place zeros of the max terms which are represented. In min terms we place them as 1, in max terms we place them as zeros. So 3, 5, 6, 9, 10, 11, 13 in this block, 19, 21, 22, 25, 26, 27, 29 in this particular block. Okay, again I would go with the grouping and let's see the result of groupings. Okay, look at this. There are no isolated ones which are found. Okay, now first grouping, let's look into the grouping here guys, which will make the concept very clear. Into the grouping, Okay. Now, what is the first group that they, so the first group here is cells 9, 13, 25 and 29. Okay. So, this is that group 9, 13, 25, 29. Okay, common. So, A0 and A1 gets cancelled. So, what would I be left with? I would be left with this particular column, which is D plus E bar. D plus E bar, and we look into the rows, C gets cancelled and we left with the B bar. So, the total output is B bar plus D plus E bar. Okay. Now, when you look into the second grouping, it is covering cells 3, 11, similarly here 19 and 27. Okay. So, when you look into this particular cell, A0 and A1 gets cancelled because both of them are common in both the blocks, and when you look into this rows, okay, I will cancel B and B bar. So, I will be left with only C bar. Okay. So, C plus D bar plus E bar. Okay. Now, when you look into the third grouping, what is the third grouping? Cells 5, 13 and then what? 5, 13, 21, 29 here. Okay. So, A0 and A1 gets cancelled and I will be looking after rows and columns, with which I will get my result as C bar plus D plus E bar. Okay. Now, look into terms 6 and 22. 6 and 22 is a 2 square. 6 and 22 is a 2 square, wherein A0 and A1 gets cancelled and I will be left with what? B plus C bar plus D bar plus E. Okay. So, that is what represented here. Okay. Next group is 10, 11, 26, 27. Okay. A0, A bar gets cancelled. I will be left with B bar plus C plus D bar. And then finally, I have 22 and 23 only in the second block. 22 and 23 only in the second block, hence I write that as A bar. I am including this A bar plus B plus C bar plus D bar. Okay. Finally, I would write the sum, minimize the sum equation by taking a product of all these groups, because I am going with POS expression. Okay. So, this is another example of solving the 5 variable Boolean function using K-maps. Okay. Let us look into another example. See, for easy access I have put it this way. So, when you look into this, I have another 5 variable K-map. When we look into this, look at the group 1. All of you look at group 1. So, 0 and 16 is forming group 1. Okay. Next, what is group 2? Group 2 is isolated here. I do not have any combination for group 2. Similarly, for group 3, see, there is nothing in 1, 4, 13, 17 for me to group here. Similarly, I do not have min term in 21. So, I do not have any option. So, group 2 is a isolated term. Group 3 also there is nothing in 6. So, it is also isolated. And when you come for this is common in both the groups. So, that is group 5. And when in group 4, this is another pairing. Okay. So, this is how we do the grouping in the, okay. So, this is how we do grouping in 5 variable K-map. Okay. Now, when you want to represent this particular K-map in your paper, you look into the procedure. First, fill the cells which are given in the POS with 0. Then group the adjacent cells in the group of adjacent cells in group of 1, 2 and 4. Now, in this particular example, there are 5 groups. Okay. So, 0, 16 are grouped. Look at this. Cells 0 and 16 are grouped, and the output of that particular group is B plus C plus D plus E. Okay. Why is it that? So, this is B plus C, this is D plus E. So, this grouping result is B plus C plus D plus E. Okay. So, as it is common in both, I am not including one because A0 and A1 gets cancelled. Okay. Now, cell 5 in group 2 and the min term of this group. Okay. When you look at this, 5 is isolated. So, what would be the result? A plus B bar, A plus B plus C bar plus D plus E bar. Okay, the same result is given here. Similarly, we write it for each and every. Okay, so this is your SOP. So when you go for SOP, we will go for product terms. Okay, sorry, I was confused, it is product term. Okay, so at the end, for the minimized Boolean expression, we would add all the product terms, that is summing of all the product terms. Similarly, when you go for POS, we would place zeros and then check for grouping, check for isolated ones, so isolated grouping or 2 variable grouping, 4 variable grouping and all that, and then reduce it into the given expression. Okay, so in the previous case, we had ones in the cells, that is min terms, hence we get product terms. In the next example, we have capital M, that is max terms, hence we represent zeros and the result would be sum terms. Okay, the sum terms are represented here in the given equation. Okay, so this is all about your K maps. Okay, so we are done with solving many examples on Boolean function reduction using K map, wherein we have covered 2 variable, 3 variable, 4 variable and also 5 variable K maps. Okay, and the last topic of the third unit, okay, is all about NAND and NOR implementation. Okay, so before we start with NAND and NOR implementation, let us quickly recap on what did we study about NAND and NOR. So we have seen that NAND and NOR gates are called as universal gates, and we have seen that digital circuits are frequently constructed with NAND and NOR gates rather than AND and NOR. Okay, because as I told you, NAND and NOR are called universal gates and they are easier to fabricate with other electronic components in digital ICs. Okay, as I told you, NAND and see basic operations are AND or NOT, right? So for AND or NOT, we need to take 3 different gates, but combination of these 3 AND or NOT are into only 2 gates, which are called universal gate. Okay, that is NAND, which is nothing but AND with inverter, NOR, which is nothing but OR with inverter. So when you are designing digital circuits or when you are designing integrated circuits, it would be more good and better if you use NAND and NOR representation of the circuit, because they reduce the number of components. So when you reduce the number of components, the size of the device, the cost of the device, the functioning of the device or speed of the device would be increased. Okay, cost will be reduced, size would be reduced, speed would be increased. Okay, now as you look into this single gate type, suppose if I use only NAND implementation of the entire logic circuit, okay, in normal AOI logic is AND or inverter logic, we require more ICs, so we have to spend more amount of time, money. If you go for only NAND logic, we may use less ICs, so cost of the device would be reduced. The same thing goes with NOR gate also. So by using NAND or NOR implementation, you can give a revolutionary change in the way the digital circuits will be designed. Okay, so we've also seen how do we design inverter using only NAND gate by just shorting the 2 inputs. We have seen how do we design AND using only NAND. We've also seen how to use OR using only NAND, and we've also seen how to use only NAND NOR using only NAND gates. Okay, we have discussed about this in the last sessions. Similarly, we've also seen how do we implement inverter and OR and NAND using only NOR gates. Okay, yeah. So we've also looked into this law, which is called as De Morgan's law. We have De Morgan's law theorem 1 and 2, wherein we have seen A plus B bar is equal to A bar into B bar. That is, when you are taking the whole complement of a sum term, when you are dividing it, we will have the product of individual complements, right? And in the second case, when you are taking the complement of the product term, so complement of the product term will be equal to sum of individual complements of the terms. Okay. Now when you look into this particular logic in terms of the circuit, what you can observe here is, please understand this because this is very important. So this particular gate is called as NOR gate. NOR gate equivalent of AND will be inverted input AND gate. What is that? NOR gate equivalent circuit of AND will be inverted input AND. Similarly, OR gate equivalent would be inverted input and inverted output. You can apply the inputs, solve that, you will be getting the expression. Okay. Similarly, inverted AND is equal to NAND is equal to inverted input OR. Okay. Just remember these two logics. Okay. NOR is equal to inverted input AND NAND is equal to inverted input OR. Okay, these two are very important for us to process further. Let me explain you. Okay, now given a Boolean function, given any Boolean function, there are two ways in which we can design a circuit. Okay, one is AOI implementation, that is AND OR and inverter implementation. By using this, the number of gates that we use may be more, or we may have to use more number of ICs. So hence, to avoid that complexity, we will be using NAND implementation. Okay, when a function is given, we will first draw the AOI implementation and convert that AOI implementation of the given function into only NAND representation. Let's see how do we do that. Okay, now as I told you, you have to remember these two things, these two illustrations. Okay, when you go for NAND, okay, so NAND is what? Complement of the inputs, right? So this is the logic symbol. When you want to put that same with OR, what do? We put it as inverted OR. Okay, that is what I told you. When you have this NAND, the equivalent circuit of NAND is input inverted OR. The same thing I have put it here. Okay, that is we put bubbles which represents the inversion in the see here NAND is nothing but output bubbled of AND gate. Similarly, the equivalent circuit is input bubbled of the OR gate. So this will be what? X bar plus Y bar plus Z bar, and when we apply De Morgan's theorem, when you have individual complements and addition terms, when you apply De Morgan's theorem to this will be X, Y, Z whole bar, which is again a NAND gate. Okay. Now look at this example. Okay. So first I have this expression. What is that expression? I have my expression as F is equal to AB plus CD. Okay, let's take this expression. All of you look at the board. AB plus CD is the given expression. Okay, so how do I draw the logic circuit for this? I take A input, B input. As this is a product term, I take a NAND gate, AND gate, and I have C input, D input. That is also a product term. I'll get another AND gate. Both these are added, so I'll take a OR gate. Okay, now this would be F is equal to, here my output will be AB, here my output would be CD, and here my output would be AB plus CD. Okay, now how many ICs do I want to implement this Boolean function? I need two ICs. Why do I need two ICs? One IC of what? AND gate, and another IC of what? OR gate. So I am using two ICs for designing this particular function in AOI format and or inverter format. Okay, now I don't want two ICs, I want to reduce the size. So what do? I go for NAND implementation of the given circuit. And look at this, what did I do here? For NAND implementation, what we do is, look at this. So for NAND implementation, I put a bubble here, I put a bubble here, and I cancel this bubbles with this. Okay, so this would be what? AB, this would be CD. Okay, now this bubbles and this bubbles gets cancelled, so there is no problem when I use both of them together. Okay, now as I told you, the inverted input OR can be replaced with what? A NAND gate, right? So in the third step, as you can see, what did I do? I have replaced with this inverted input OR gate with NAND gate. So this is using AND and OR, which requires two ICs, but this is with NAND gates which require only one IC. What is that IC? One IC of NAND gate. Now you would be wondering about, madam, here we have, see, these are components. Okay, these are logic gates, but inside one IC you will have n number of logic gates. Got it? So inside one IC you may have 4 NAND gates, 6 NAND gates, or 8 NAND gates. So we need only one IC of NAND gate for representing this Boolean function. Hence the number of ICs are reduced from 2 to 1 when you implement this Boolean function using only NAND gates. Okay. Similarly, this is another example. Okay, function f is equal to 1, 2, 3, 5, 7. Minimize the function and implement with NAND gate. You will be asked the question like this. You are asked to reduce the given Boolean function and then implement that with the NAND gate. Okay. So first what do? I have till 7. ABC is not mentioned here. So I have variables till 7. So it is 3 variable K map. Okay. So I will draw the 3 variable K maps. 1, 2, 3, 4, 5, 7. I will go with, this is min term sigma. So I will place ones and I will group, and this is the minimized group that I got. X y bar plus x bar y plus z. Okay. Now what do? I draw my function first. Okay. X y bar x bar y plus z. Okay, and that I connected to a inverted input OR gate, and that would be connected to a NAND gate. Okay, so this is how we convert any Boolean function into only NAND implementation. Okay, now when we go for NOR representation, NOR is something like this. When you go for 3 input variable, I have x, y, z inverted x plus y plus z bar. So this NOR is converted to inverted input AND. So what is inverted AND? X bar, y bar, z bar. So this also can be represented as what? X plus y plus z bar. That is De Morgan's theorem. Okay. Now this is another example. So same rules of NAND that we have applied. We apply the same thing. We will replace NOR with inverted input AND. Okay. Let's look at the example. We'll go for 3 level. See, this is level 1, this is level 2, this is level 3. Okay. 3 level implementation of NAND gate. I have expression AB bar, product term, gate 1, CD bar, product term and gate 2, and then I have addition term, hence I am taking OR gate. Both of them are added, another OR gate, and then these two terms are ANDed together. This is one AND gate. Okay. Now how many ICs do I need here? I need 2 ICs, one OR gate IC, one AND gate IC, but I don't want that. I will go for NAND implementation. So what is step 1? I will replace this NAND with inverted bubbles and all this stuff, and then I will convert. See, simply I am converting it into mixed notation by converting AND into AND invert and OR into invert OR. Okay, and after that I am replacing all the gates with only NAND gate. Okay, I know it would be a little confusing, but you need practice. Okay, if you just understand these 2 things, it would be easy. Okay, what are those 2 things? Yes, NAND is replaced with inverted OR, and NOR is replaced with inverted AND. That is, OR gate output input will be equal to bubbles in the input of AND gate. Okay, so this is another example of NOR, and then same function. Let's use AB bar plus CD bar plus A bar plus B, same function. Let's use NOR implementation. I am putting, as it is AND gate, I am putting bubbles in the front, and I am taking the same thing in the, so I am just converting it into mixed notation of NOR, and then finally I will replace all of them with only NOR gates. Okay, so this is how we implement any digital logic circuit. Okay, given a function, we will try to reduce the function and implement that particular function using AOI representation, or using only NAND representation, or using only NOR representation. But we prefer NAND and NOR implementation because with this we can reduce the number of ICs such that we will reduce the cost and the size or the weight used by that particular electronic device. Okay. So in 3rd unit we have started with fundamentals of digital circuits, we have compared analog and digital circuits, and then we have seen some Boolean laws. We have started with Boolean algebra where we have seen some laws and theorems, and then we have seen what is sum of product representation, what is product of sum representation of a Boolean function. We have seen logic gates, and we have also seen types of logic gates. Okay, basic logic gates, universal gates and special gates. AND or NOT are basic logic gates, NAND and NOR are universal gates, XOR and XNOR are special logic gates. So once we are done with logic gates, we have started with designing logic circuits. So before we actually go with designing logic circuits, we require we should try to reduce the given expression. Okay, so there are two ways in which you can reduce the given Boolean function. What is the necessity when you reduce the Boolean function? As I told you, the number of components will be reduced, size of the device will be reduced, cost of the device will be reduced, and the speed would be increased. So there are two ways in which you can reduce the given function. One, using Boolean laws and theorem, but there is a disadvantage with that. That is, when you try to reduce the given Boolean function with Boolean laws and theorems, not everybody gets the optimized solution, and it would be difficult for us to understand which law to be put in that particular situation. Hence, we go for the second method of solving the Boolean function or reducing the Boolean function, which is called as K-map or Carnot method. So, we have 2 variable K-map, 3 variable K-map, 4 variable K-map and 5 variable K-map, right. So, once we are done with that, we have also seen don't care conditions. Okay, what don't care conditions are, what are their importance, and how do they help us in solving the reduction of Boolean function. And then in the last, we have discussed about NAND and NOR implementation of the logic circuits. Okay, so with this we are done with unit 3. Thank you.